All right, so this is 5.2b homework. There's no notes for today. We just kind of worked on more problems. So I'm going to do some of these homework problems with you. And let's go ahead and get started. So if you look at number 6. Number 6 is a problem that we've done in the past. But, I mean, not exactly like it, but pretty similar because I definitely think that this is the harder side. It's got some fourth degrees on there. So let's rewrite that side. So secant to the fourth x minus tangent to the fourth x. Now, what's the biggest step on this problem is recognizing the fact that this is indeed a difference of square, because a difference of square I define as you have the ability to take the square root, you have the ability to take the square root separated with a difference. So if I look at this side, I can take the square root of secant to the fourth. I can take the square root of tangent to the fourth. They're separated with a difference. So when I do that, it's separate with a plus, separate with a minus. So the square root of secant to the fourth is secant squared. And the square root of secant to the fourth is secant squared. So I put it here, and I put it here, and then the square root of tangent to the fourth is tangent squared. So I put that here and here, okay? So this is me taking the difference of squares of secant to the fourth x minus tangent to the fourth x. Now that I've got some square terms, I would love if this matched to one of my Pythagorean. So if you look at your Pythagorean identities, one of these groups matches exactly to a Pythagorean identity. So go ahead and scope out your Pythagorean, see which one it is. So it's this guy right here. If you look at your Pythagorean, this equals 1. So I can say times 1. I don't really need to write this times 1 because multiplying times 1 is kind of a redundant thing. So I'm just going to say this no longer is here because when you multiply times 1, it's not really necessary. So I will rewrite only this. And I don't need to include the parentheses anymore because if I multiply times the 1, it's really not going to do anything. All right, so if we look at now where I'm trying to end. I'm trying to end with 1 plus 2 tangent squared. And I have a tangent squared, so that seems like it's a good thing. But this secant squared right here is not necessary for where I'm trying to end. So what I'll do is, again, I can say, well, secant squared has an equivalent statement. And I can say that secant squared is the same thing, so looking at my formula chart, as 1 plus tangent squared. So this is on my formula chart that secant squared equals 1 plus tangent squared. And then I still have this plus tangent squared. So this is staying the same, and I changed this according to Pythagorean theorem. Well, now, mathematically, when you have plus tangent squared plus another tangent squared, you have a total of 2 tangent squares. And don't forget about this original 1. Nothing happened to that 1, and you have plus 2 tangent squared. Okay? All right, number 8 is one of those problems that if you get a common denominator, it actually gets you nowhere. So I'm not going to show you that. I've already shown you that in class, but I know everybody's first step here is probably to get a common denominator, and it leads you to a path of destruction. It's just nowhere good. So think of something else that you can do. Well, if you've got secant squared in the denominator here, then instead of writing secant squared, let's write cosine squared. And instead of writing cosecant squared, let's write 1 over sine squared. Well, don't really like having fractions over fractions. So when I rewrite this, what I'm going to do is change this to cosine squared over 1. And that goes away. So this whole thing just became cosine squared. For that same reason, this becomes sine squared, which is an identity equal to 1. All right, let's go on to the back. Okay, if we do number 9. Actually, you know what? We did a problem exactly like 9, so I'm going to skip that problem, and let's go on to 10. 10 is a little bit harder anyways. So obviously this is a much harder sign to start with, so that's where I'm going to start, so go ahead and rewrite it. And when I'm writing this, I'm kind of looking at all of my 1 pluses, and I'm thinking about Pythagorean theorem. So if what you're thinking about is Pythagorean theorem, you need to realize the correct Pythagorean theorem is sine squared equals 1 minus cosine squared. So why did I choose that one? Well, I chose that one because I keep seeing 1 minus cosine. So this is as close as I can get. But they are not entirely the same, right? This is 1 minus cosine squared, whereas this is only 1 minus cosine. So what we have to do is use the difference of squares rule here. So instead of writing 1 minus cosine squared, I can think 1 plus cosine and 1 minus cosine. So this is the factored version of this. So what this represents is the difference of squares of this. Okay? So what we're going to try to do is use that in helping us. So when I'm looking at my problem, I'm going to group this because I kind of see that this matches this thing right here. And I know that if I multiply times its conjugate, that's what this is called. These guys are conjugates of one another. If I multiplied times its conjugate, I would get up to 1 minus cosine squared, which would lead me to sine squared. So I'm going to choose a denominator to multiply this by of 1 plus cosine x. So it's not always that when you get a common denominator, you just look at what the other one has. That's not always the best method for you, because if this is 1 minus cosine x, if I multiply by its conjugate, 1 plus cosine x, then I get 1 minus cosine squared, which is actually sine squared. So what I've done in this step right here is I have made an extremely clever version of a denominator sine squared. Okay, all right, now on the top, go ahead and distribute. So sine times 1 is sine, and sine times plus cosine is plus sine cosine. All right. This is the hardest step. That step that we just did is the hardest step. Realizing that instead of just switching the denominator, you have to do its conjugate right here. All right. Now in this next step, think about why we did all this so that we could get sine squared in this denominator. Well, this is already sine, so if I just multiply times sine over sine to get that common denominator, I would obtain the easiest version of the common denominator. So I do in fact get the sine squared that I wanted on the bottom. And on top, once again, you do have to distribute. So that becomes sine. And now I have a minus cosine. Sine times minus cosine makes negative sine cosine. All right, so the reason why we get common denominators is to add across the top. So when you add, you want to add like terms. So a like term, so I have a sign here plus another sign. Sine plus sine makes 2 sine. Okay, now let's look at sine times cosine plus negative sine times cosine. That goes away. I have a positive sine cosine, a minus sine cosine. Goes away. All right, so now I have over sine squared. Well, I know that sine over sine squared is really like sine times sine, so I can cross off that square with that, and I'm left with just 2 over sine. Well, if you understand your reciprocals, you know that over sine means you could actually put that guy on top, but when you put him on top, because you're reciprocating it, you can't use sine anymore. You'd have to use cosecant. Okay? All right, let's do number 11. So number 11, you could argue whichever side you wanted to. I typically start with fractions if I have the choice because I have a lot of techniques with fractions. Plus, when I look at that left-hand side, I see conjugates written all over it. So remember, conjugates is 1 plus sign and 1 minus sign, which I actually see the top and the bottom already with that. So I'm going to start with this side. I definitely think it's probably the easier side. All right, so that is the step I'm going to take. I see half of a difference a square here. Remember that the full difference a square, let me write this out. The full difference a square would be 1 minus sine squared, and that makes 1 plus sine, 1 minus sine. So the fact that I see the 1 minus the sine, if I multiplied times the 1 plus the sine, then I would have exactly this, which will probably end up helping me out. So that's called the conjugate, 1 plus sine. So no, I'm not even trying to get a common denominator here. I just know that when I multiply its conjugate, it helps me out. All right, well, unfortunately, that's good and fine for the denominator. That's going to make 1 minus sine squared because these are the difference of square pair. But this numerator is not difference of squares. It's 1 plus sine times 1 plus sine. And you may know a shortcut to do this, but I'm just going to go ahead and do it. You have to FOIL this because there's not a difference of square rule for it. You're going to have to do that. So 1 times 1 is 1 plus sine plus sine, and then plus sine squared. Okay, and now I have all over. So on bottom though, remember we can go ahead and take the shortcut. If you FOIL this, you should get the same thing, but the shortcut is I know that that's difference of squares, so I can go ahead and write that as 1 minus sine squared. All right, I'm going to I'm going to run out of room if I don't start taking a few shortcuts. So what I'm going to do here is I'm just going to say this makes plus 2 sine x. I don't want to spend a whole nother step writing that. Okay, my next step is going to be kind of also another shortcut, or not shortcut, but I don't particularly feel like writing a whole nother step to say that this is cosine squared. Remember that that's one of the main reasons that we did all this, is to shorten that denominator. All right, so this is where we're at. Now, in this almost last step, what I'm going to do is I'm going to break this up into separate fractions. The reason that I'm doing this is because I see that I have something plus something plus something. And so I don't need to see like all this one big fraction. So I'm going to write 1 over cosine squared. Then I have plus 2 sine over cosine squared. And then I have plus sine squared over cosine squared. All right, so 1 over cosine squared is really secant squared. So I'm just going to reduce each one. Plus, now, sine over cosine squared. Well, sine over cosine times cosine. And I've got a 2 also. So what this really makes is the 2 is going to stay a 2. Sine over cosine makes tangent. And then 1 over cosine makes secant. And then for my last, plus sine squared over cosine squared, that's tangent squared. Okay. So I kind of would like to think that I'm done, and if you look, you're actually really close. This middle piece is represented in what I have, but I don't have these two guys yet. I do have a secant squared, so I'm pretty close there, but I don't need tangent squared. So looking at your formula chart, instead of writing tangent squared, you could write secant squared minus 1. So I'm just going to rewrite everything else, but what I'm doing is instead of writing tangent squared, I'm writing secant squared minus 1. So this is actually the final step because now secant squared plus secant squared makes 2 secant squares. I have this middle piece, and I have the minus 1. Okay? All right, that was all number 11. I'm going to pause this so I can erase it. Okay, number 12. So I definitely think using the addition subtraction side, this side right here, makes it easier because addition and subtraction usually complicates something. And so you start with the more complicated and then you go to the easier. Now this is a perfect greatest common factor problem because I've got cosine squared in one group, cosine to the 4th in the other group. I've also got sine in both groups. So when you're thinking about greatest common factor, you're kind of looking these as groups of each other and seeing what they both have. So they both go as high as cosine squared, but make sure you get the greatest common factor. They both also have a sine. So pull out both of those things, not just one. Now open parenthesis. All right, so we have to say this times what here gets you this. Well, the thing is that you've already represented cosine squared, you've already represented sine. So you still have to multiply it by something, but this is when you just multiply it by 1 because when you multiply it by 1, it stays the same. Then we want to have that minus sign that you see. And now multiply cosine squared sine times what here gets you cosine to the 4th sine. So now I say, well, cosine squared isn't quite cosine to the 4th. I have to multiply by cosine squared because now cosine squared times cosine squared is how I get to cosine to the 4th. But I've already got the sine because I only wanted sine, so I don't need anything else there. And let's close that parenthesis. Well, at this point, 1 minus cosine squared is sine squared. We all know that. So I can say cosine squared times sine squared. And this makes sine cubed. Okay. Oops. So that's that. I didn't reverse the order. You don't have to. I mean, I can see that that works, but that's that. All right, let's go on to 13. Now, I definitely think fractions, the fraction is harder, so that's where I'll start. And again, hopefully what you're thinking about as you're writing this down is how to solve this. This is a half of difference of squares. If you multiply by its conjugate, so I've said that word a whole bunch in this homework. Conjugate is when you see half of the difference of square. Then I can finish off this problem. This problem is actually just a one-stepper. After you figure that out, now the reason why we do conjugates is because this is an easy foiling. You don't actually even have to foil it. You can just say it equals secant squared minus tangent squared. And on top, I have secant x plus tangent x. Now, this guy is a Pythagorean identity. And that Pythagorean identity actually makes just one. And on top, I still have the secant x plus the tangent x, which is exactly where I want it to be. Okay. All right. Number 14 is our last one. So on number 14, this is like our factoring problem, but there's a big difference between this factoring problem and the one we did the other day. This one has secant squares and has tangents, which isn't really something that you can factor. That's like saying you want to factor x squared plus a squared plus, you don't factor that when these are different terms. So you can't factor that yet, but we know how to change trigs according to Pythagorean theorem. So according to the Pythagorean theorem, I don't have to use secant squared. According to Pythagorean theorem, instead of secant squared, I can use 1 plus tangent squared. Okay? Now I'm still going to continue to write the minus 6 tangent x and the plus 7. The reason why I did this step is so that now all I have are tangents on top. And for that same reason, let's go ahead and also change the bottom. So instead of secant squared, I'm going to again write 1 plus tangent squared. And I'll just write the minus 5 exactly how I see it. Well, before we factor, we do need to combine some like terms. And so this is now going to become tangent squared minus 6 tangent. 1 plus 7 makes 8. And tangent squared minus 4. All right, now I can factor because now I have only in terms of tangent. So you're going to factor the top and then you're going to factor the bottom. So when you factor the top, this is a true factorization because you have tangent squared, tangent number. So what makes tangent squared? That goes here and here. What makes 8 and adds to negative 6? That goes here and here. Well, tangent squared is simply tangent times tangent. Now, multiplies to 8, yet adds to negative 6. So I know 8 can be 1 times 8 or 2 times 4. Well, 2 and 4 can add to negative 6 if both of those numbers are negative. Okay, and now this bottom part, hopefully, even though we haven't seen this, this is a difference of square, just like all the other ones are. Because if I need to add to that's a perfect square. This is a perfect square separated with a difference. So that's tangent x plus 2. Separate with a plus, separate with a minus. And now I could officially cross off, and I end up with tangent x minus 4, which is where we want it to be. Oops.